Okay, so I wanted to record a couple videos here to demonstrate beam design. Quiz 3 is going to consist of two beam design problems, a steel beam design and timber beam design. And so in this video we'll look at problem 1617 from the textbook in order to demonstrate the steel beam design process. So looking at this beam, first of all, we have two different types of loads. We have a distributed load of 1 kip per foot, and we have two concentrated loads, 20 kips each, and they are applied at third points of the beam. So you can see here that the overall length of the beam is 24 feet, and the concentrated loads are located at 8 feet increments. So whenever you're presented with a beam, we need to first find the maximum moment. And if you don't have it memorized, you can go to Appendix H to find the appropriate formula. So like I said, we've got two different types. The first type here is a distributed load. So the maximum moment occurs at the center of the beam, and that's equal to WL squared over 8. So our moment is going to be WL squared over 8 plus we've got the moment caused by the two concentrated loads, the 2-point loads. So we've got to refer to the appendix and see if there's a situation that corresponds with that. There's 1-point load at midspan. There's another point load offset. Aha, here we go. Two equal concentrated loads symmetrically placed. So the distance A is 8 feet, and the magnitude of the load is P. What we want to find again is the maximum moment, which is going to occur basically anywhere in between these two loads. When put into combination with the distributed load, that means our maximum moment is going to occur at midspan. And so that maximum moment is just equal to P times A. So I've got WL squared over 8 plus PA is going to give me the maximum moment on this beam caused by these two different types of loads. So the W distributed load is 1 kip per foot. The overall length of the beam is 24 feet squared over 8 plus P, the concentrated load, is 20 kips times A, the distance A is 8 feet. So let's calculate that and see what that equals. All right, so I punched that into my calculator and I'm getting 232 kip feet as the maximum load applied to this beam. Now, the maximum moment applied to the beam. Now, if I want to convert that into kip inches, remember this is a moment. This is kip feet. It's not kips per foot. It's kip times feet. So feet are on the top. So to convert, I got to put it on the bottom. So for every 1 foot, there are 12 inches. So I am multiplying here by 12, not dividing. That's a really common mistake I see students make. A simple unit conversion problem. So if I take 232 times 12, that gives me 2784. 2,784 kip inches. That's my maximum moment. So then I want to find what is the plastic section modulus required for a beam to resist a moment of 2,784 kip inches. So my formula here, my AISC ASD formula for beam design tells me 1.67 times the moment divided by the yield stress. Okay, so that's going to be 1.67 times 2784. That's a 7. Divided by the yield stress. Wide flange beams almost always have a yield stress of 50 KSI. Okay, so that is equal to 93 inches to the third is how big the plastic section modulus needs to be. So we need to then go to the appendix to find a wide flange that will be strong enough. Okay, so I've got my appendix here. I am looking for a wide flange with a section modulus of at least 93. So this is Appendix A here, but there's actually an appendix that has the members ordered according to their plastic section modulus, which is what I want to use. I'm looking for one that's at least 93, so they're sorted in order here, and it looks like W18 by 50 would work. But the way this table is organized is if I go up to the next bold entry, that is more efficient. So I've got an 18 by 50 or a 21 by 50. So they each weigh 50 pounds per foot, so their difference in weight is no different. But the 21 by 50 does have a higher section modulus for the same weight, and it has a fairly significantly higher moment of inertia, which is going to help us out when it comes to deflection. So it just makes sense to use the W21 by 50, assuming that there are no clearance issues, that having a 21-inch deep beam isn't going to cause someone to hit their head on the underside of the beam when they walk below it. It just makes sense to go with the one that has the same weight but higher section modulus and higher moment of inertia. So we'll use that one. We'll try, I'm going to write down here that we are going to try a W21 by 50, and that has a plastic section modulus, Z sub x, of 110. That's inches to the third. And a moment of inertia, I sub x, moment of inertia about the x-axis, of 984 inches to the fourth. Okay, so I've chosen a beam that I think will work, but I should now go back and check the self-weight, make sure that the moment caused by the self-weight of the beam doesn't cause this beam to fail any of my design criteria. So a couple different ways to do that. One is to just find the additional moment caused by the self-weight alone, and then add that back up here to the moment we had previously calculated, and then find out how much additional section modulus is required. Or just find the moment, find the section modulus required for that additional moment, and add it to here. It's just really a difference of the order in which we do it. So self-weight is always a uniformly distributed weight. So the formula there is WL squared over 8 for the self-weight. And the self-weight is in the designation of the wide flange. We chose W21 by 50. So that means it has a weight of 50 pounds per foot. But we would prefer to deal in inches. Well, I tell you what, let's calculate the moment first, and then we can convert to inches. So that's going to be 50 pounds per foot times the length of 24 feet. squared divided by 8. So let's check that and see what that equals. So that gave me 3,600, which seems like a big number, but remember we were using pounds here. So this is 3,600 pound-feet. Now if I want to convert that into kip inches, I need to convert, for every 1 foot, there are 12 inches, and for every 1,000 pounds, there is 1 kip. And so that equals 43.2 kip inches. So what I was saying earlier is I can either then take this additional moment from the self-weight and add it to the original moment we calculated and find a new ZX, or just take this moment by itself and calculate how much additional section modulus is going to be required for the self-weight, and then add it to the original requirement of 93. So I'll do it that way. I'll take my ZX is equal to 1.67 times the moment of 43.2 divided by 50, and that only equals 1.44 additional inches to the third of section modulus required. So if I add that, I could even round that up to 2. Let's say 2 plus the original 93, which was required, means I now need to make sure I have at least 95 inches to the third of section modulus. Well, if I go back and look at the W21 by 50 that I selected, it has 110. That's what we are providing. 110 inches to the third of section modulus. So is a W21 by 50 still good? Yes, it is. So I think I'll stop there and continue this problem with a second video. So just to quickly recap, we found the moment applied to the beam. We used that to find the required section modulus. We chose a beam from the appendix. We calculated the self-weight moment. We then found the additional section modulus required by the self-weight and compared that to what was provided by our originally selected beam, and we found that it is still good. So now we need to check deflection, shear, and I think that'll be it. If we check deflection and shear, it should be good. So we'll do that in the next video.